so close to the beginning was actually QICS. So it's going to tell us about depth and flow investment based quantum computing.
Okay, thank you very much. So welcome to this memory-based quantum computation session. So I'm going to talk about depth and flow. So what does it mean? So depth is a concept which is coming from computer science, from complexity. And depth means the parallel time. Okay, so we are considering this parallelization. And in terms of the discussion-based quantum computation, model is very interesting in terms of parallelization. Okay. And so we are going to talk about the depth, the parallel time in this model. And in terms of that, so intuitively this model is interesting for parallelization because it takes the bit of the initial entanglement. Okay, we use the initial entanglement in order to realize parallelization of the quantum operations. And in order to study the depth in this model, we are going to use the flow, which is a notion which is coming from graph theory. So we are taking the underlying graph states, that is the graph which is representing the initial entanglement, and by defining a notion of flow on this underlying graph, we are talking about the depth and the properties of MBQC, of measurement-based quantum computations. And it turns out that there are also some connections with causality, the more physical concept of causality. Basically, the idea is that the causality is the limit to the parallelization. If you have two operations such that there is a causality dependency between these two operations, okay, then it means that you cannot do them at the same step. Okay, you cannot parallelize them. So the causality is the limit to the parallelization. That's why this causality is coming to the picture here. Okay, so some general comments about the depth. So when we have a circuit, so it can be a quantum circuit or a classical circuit, any kind of circuit, we can define the size. The size is the number of gates. So here we have 6 gates. And this size is the sequential time. So if you just have one processor, you need 6 steps in order to run this circuit. Okay? But it turns out that here, for instance, these 2 gates are acting on distinct qubits or bits. So it means that you can perform these 2 gates at the same time. So if you have several processors, if you allow parallel computation, then you can do these 2 operations, then this one, then these 2, and finally this one. So what is important? What is the time of the computation? It's the number of layers. Okay. So here there are 4 steps. So the depth of the circuit is the minimum number of layers, and it turns out that we can equivalently define the depth as the largest sequence of dependent gates. So here is the example. So here there is a dependency between these 2 operations because they are acting on the same wire. So we should apply this one first and then this one. Another dependency here, another dependency here. And if you look at the largest sequence of dependent gates, you obtain exactly the depth of the computation. Because when you have such a sequence of dependent gates, this is the limit to the parallelization. Okay, so here in this example, the depth is 4. Another general comment about parallelization. The parallelization is a hard task in general, in classical computer science, in quantum computer science. And in fact, there is no obvious connections between the size, the sequential time of the computation, and the depth of the computation, the parallel time in general. And in order to illustrate the fact that it's a hard question, we have this open question in the complexity theory, which is that is P equal to NC? So P, probably know P. So P is the class of problems that can be solved in polynomial time. So class of problems that can be solved by polynomial size circuits. NC is the class of problem that can be solved by a polylogarithmic depth. So
there's something with your mic.
This?
Yeah, that's
great. Okay, so here NC is the class of problems that you can solve in polylogarithmic depth. So it means polylogarithmic means that the depth is bounded by something like means that the Pauli time is logarithmic, it's an open equation. Okay? And it's expected that it's true. That is false, sorry, that there are some problems that cannot be efficiently parameterized. Okay, so now, after this brief introduction, these remarks, what's the plan? So, first, I will start with the presentation of the measurement calculus, which is a formal framework for measurement-based quantum computation. And using this formal framework, we will be able to talk about the size and depth of a measurement-based quantum computation. Then we focus on these interesting questions, which is that when we have a given resource, a given entangled state, can we use this entangled state in order to make a useful, in order to do a useful measurement-based quantum computation? Okay, can we use this resource for a measurement-based quantum computation? And if it is the case, if this entanglement can be used to do a measurement-based quantum computation, then what is the depth of such measurement-based quantum computation? And what is the minimum depth of such computation? Okay. And the second part of this presentation will be dedicated to the comparison of the power of the measurement-based quantum computation with the other models of quantum computation, especially the quantum circuits. Okay, and we'll compare the power of the measurement-based quantum computation with other models of quantum computations. Okay, so first of all, the measurement calculus. So it's a formal framework for describing a measurement-based quantum computation. So we are using four commands, four kind of instructions in order to describe a measurement-based quantum computation. So the first two commands are used to describe the initial entangled state. So first we use ni in order to say that we are working with an ancillary qubit. So at the beginning we have the input. So let's say that we have one input, one qubit as the input. This is the input of the computation. So we are adding several ancillary qubits, so using this command ni, so n2, n3, in order to add ancillary qubits. Then we are creating entanglement between all these qubits using the command eij, which is creating entanglement using between I and j. So at the end of this step, after the application of several eij, we obtain the initial entanglement, the initial graph state, cluster state. This is the resource of the computation. So now we are ready for the measurement-based computation, so for the measurements. So we can apply the measurement ni alpha, so which means that this is the measurement of the qubit I, so in that case the measurement of the first qubit. And this measurement, the basis of this measurement is parameterized by a number alpha. So in that case alpha is equal to 0. But in general alpha is an envelope. And we perform the measurement in these bases, plus alpha minus alpha, where plus alpha minus alpha are given here. Okay? So we perform this one qubit measurement, one qubit I, and this measurement is parameterized by an envelope alpha. So this measurement is producing a classical outcome. This classical outcome is called SI. It's 0 or 1. Okay? So we assume that the measurement is destructive, so we are consuming the qubit. Okay? And now we have this classical outcome 0 or 1. And finally, we have another kind of command, which is the correction. We can perform corrections. The correction is just a Pauli operation, so which is applied xi, sj, so it's applied on qubit I, and it's classically controlled. It's parameterized by the classical outcome of some previous measurements. So this is a correction. Okay, depending on the classical outcome of some previous measurement, we are applying this Pauli operation or not. Okay. So in fact, if the classical outcome is 1, then we are applying the correction. If it is 0, we are not applying the correction. Okay. So, and more generally, this correction may depend on several classical outcomes. Okay. In that case, if there is a dependency on several classical outcomes, the correction is applied if and only if there is an odd number of ones among the classical outcomes. So this is the sum description of the computation. So this part is the description of the graph, so it's equivalent to this one. And then here we have the description of the measurements and the corrections. Okay, measurements with the angle of measurements, and then the corrections depending on the classical outcomes. So we can also list those. So measurement of this qubit, corrections depending on the previous classical outcome, measurement of this qubit, corrections, measurement of this one, and so on. And we can see that here, since we have two independent parts, we can perform the rest of the computation in parallel. At the same time, we can measure these two qubits at the same time, and we obtain the outcome of the computation. Okay. So this is the measurement calculus, the description of the measurement-based quantum computation using a sequence of commands like this. Okay, so now we are ready to define the size and the depth of a measurement-based quantum computation. So the size is nothing but the number of comments of the pattern, okay, number of instructions, like in the quantum sequence, okay, just the number of instructions. And the depth of the pattern is the largest subsequence of dependent comments. Okay, we use a similar definition. And we say that two comments are dependent if they are acting on the same qubit. For instance, here we have creation of entanglement between, so we should read it this way from right to left. So here we are creating entanglement between I and J, and here between J and K. So there is a dependency on the qubit J. So these two operations are dependent. These ones are depending on the qubit I, because here we are creating entanglement between I and J, and here we are measuring I. But it turns out that we may have classical dependency. Here in the last case here, we have the measurement of the qubit J, and here the application of some correction in qubit I. Okay, so these two operations, these two comments are acting on distinct qubits. However, there is a classical dependency here because this correction is depending on the classical outcome of this measurement. Okay. So because of this classical dependency, the use of the classical outcome, we should first measure the qubit and then apply the correction because the correction is depending on the classical outcome of the measurement. Okay, so...
Sorry, can you remind me what is EIJ? How do we define?
Okay, EIJ means that there is an age between qubit I and qubit J, so it corresponds to the application of control Z and qubit I and qubit J. Okay, so it's a 2-qubit unitary transformation.
As control Z commute, can't you parallelize them?
Yes, it's true. It's true. So this is so I will talk about it later on. Okay. So we can define a model where you say that if two operations are commuting, then we can apply it at the same time. But it's not the usual model.
Okay.
So at the moment we just say that if two operations are acting on the same qubit, then we cannot parallelize them.
Okay, makes sense.
Okay, so for this example, so the size is 8. There are 8 operations, if I'm right. And in red you can see the largest dependent sequence. So here we're acting on 2, here on 2 and 1, here on 1. Here there is a classical dependency on the classical outcome of the measurement. Here we're acting on 2, and here there is again the classical dependency on this classical outcome S2. Okay, so here the depth is 6. So just a remark which will be useful in the second part of the presentation, but anyway, this is the definition of the depth. So just a remark here, it turns out that when we have such a comment with lots of classical dependency, in fact we don't care about the number of dependency here, we always say that this is a comment of size 1 and the depth is 1. Okay. The depth and the size of this comment doesn't obtained does not depend on the branch, does not depend on the classical outcomes of the measurements, then we say that the overall computation is deterministic. And so deterministic patterns it's a very important class of patterns of measurement-based computation because we are using these deterministic patterns in order to simulate quantum circuits, for instance. Okay, in order to simulate a unitary evolution, we need a deterministic pattern. Okay, we need that the outcome here is the same whatever the outcomes of the measurements are. Okay, this is the definition of determinism. There any question?
What's the graphical notation? You've got 3 different kinds of vertices.
Okay, so here we have a square because this is the input of the computation. So it's not an ancillary qubit, it's just the input of the computation. And this one is white because this is the output of the computation, so it means that it's unmeasured. Okay. So input square, output white, and all the other are just black dots.
What are the relationships between these 3 categories? I mean, strongly deterministic probably implies deterministic, and step was deterministic.
Is also, so it's the next one. So starting from this definition of determinism, we derive to a stronger notion of determinism. So the first one is the strong determinism, which says that, okay, all these states are the same, so this is deterministic. And moreover, we ask that the probability of each branch is 1 over 2 to the n, where n is the number of measurements. Okay, so we have the same probability to have each outcome, so it's equiprobable. And the state-wise determinism says that any partial computation of the pattern is also deterministic. So it means that here we have 2 measurements. If we apply just 1 measurement, so we are here. So if the computation is state-wise deterministic, it means that here the 2 states that we have here are the same. So more precisely, if we perform the measurement of qubit 1 and all the corrections which are depending on this measurement, then we should have the same state here and here. So this is the state-wise determinism.
Small question. So from the perspective of the unitary transform that you implement from your input to your output qubits, all 3 definitions are going to implement the same thing, right? So if it's deterministic, strong deterministic, or step deterministic in all 3 scenarios, you're going to implement just one particular unitary, right?
Yes, because you can implement unitary transformation using determinism. In fact, in order to implement a unitary transformation, you need determinism. It's just for technical reasons that we are considering a stronger version of determinism.
Would it be possible to experimentally determine between the deterministic and strongly deterministic?
Sorry?
Will it be possible to experimentally distinguish between deterministic and strongly deterministic?
So if you can repeat the computation, just looking at the probability of obtaining the classical outcome 0 or 1,
Okay.
just the expectation value, then you are able to say if it is deterministic, strongly deterministic or not. Okay, so we have this definition of determinism, and since this deterministic, the class of deterministic patterns is interesting, because we are using it to simulate quantum circuits, for instance, we are addressing the following question, which is that if you give me an internal state, so the resource of the computation, is it possible to perform a deterministic computation using this resource? So in this particular branch, the zero branch, where all the classical outcomes are zero, then there is no correction. So it means that if you take this pattern, and if you remove some corrections or add other corrections, it will not change the state phi 1, because this phi 1 does not depend on the corrections. Okay, so it's the first remark. So if moreover the evolution is deterministic, strongly deterministic, it means that all the states are the same. So it means that the phi 1 does not depend on the corrections, and the other states are not depending on the corrections because they are the same as phi 1. So it means that if we have a deterministic evolution, in fact this deterministic, the overall evolution of this pattern does not depend on the corrections. Okay? The overall evolution is characterized by just the entanglement, the initial entanglement, and the angle of the measurements. The corrections are just used to make the computation deterministic. Okay? We are using the corrections in order to ensure that this branch leads to the same outcome than the zero branch. Okay.
But that, you only need deterministic with that, right?
Okay, so I asked for strong determinism because if this branch occurs with zero probability, then there are some technical problems. Because with zero probability, you reach any state, you can put any state here. So just to be sure that this case of zero probability is not happening, we are asking for strong determinism. But it's just a technical point. Okay, so it means that a deterministic measurement-based quantum computation is just characterized by the initial entanglement and the angle of the measurements. So we call this a specification. This is the specification of the computation. Okay, we are not describing exactly how to implement it, what is the correction strategy and so on. But it turns out that with this information, it's enough to know what is the evolution, the overall evolution. Because using this information, we are able to compute phi 1, and because of the determinism, all the other branches have the same evolution. Okay, so this is, so it means that if we have a deterministic pattern, all the corrections can be abstracted away, and we keep just the description of the angle and the initial entanglement. Now the question is that if I give you a specification, okay, the other way around, if I give you a specification that is a graph with some angle of measurements, is there an implementation for this specification which is deterministic? So there are some graphs such that there is no deterministic implementation for them. So we call the specification deterministic if there exists a deterministic implementation for this specification. For a given graph and a given set of angles, if there is a pattern which is implementing this specification, we call it deterministic. Okay? And since the question that we have in mind, is that for a given resource, is it possible to implement a deterministic computation? So in fact, we only care about the initial entanglement. Okay? This is the important part. We want to focus on the initial entanglement, not on the angle of measurements. So here we add another step of abstractions, which consists in removing the angle of measurements, and saying that an open graph, that is just a description of the initial entanglement, is uniformly deterministic if for any angle of measurements the corresponding specification is deterministic. Okay, so, and now we're ready to give the decision problem. That is the problem, the question that we want to address, which is that for given open graph, that is the description of the entanglement, is it possible to implement a deterministic pattern, or in other words, is this open graph uniformly deterministic? Okay, we want to address this question. Just one remark about the uniform determinism. There is a physical interest of uniform determinism, which is that if you have a computation such that, which is deterministic, and if for some physical reason you are not implementing the angle but just the angle plus epsilon, so if there is an error in the implementation of the angle, if the computation is uniformly deterministic, then your computation is still deterministic. Okay? So incomplet of such computation. Okay. In the case where we can,
Do you have an example for a graph which has no deterministic pattern?
okay, so for instance, can we have I don't know if you have this graph, okay, which is just a triangle. The input, the output, then this one is not uniformly deterministic. Okay, we cannot perform.
But do you have any intuition if you look at the graph that you say this is this or this?
So I'm going to present a characterization of such graphs, okay, using graphical criteria. But okay, so we'll see this. So there is a notion of flow, in fact. Okay, if there is a flow from the input to the output, it means that you can transmit enough information from the input to the output such that we have deterministic evolution. This is the idea.
Yeah, so I don't know if you addressed this already, but does strong determinism imply stepwise determinism?
Strong implies stepwise. I don't think so. It implies it in general.
So how do you define partial computation? If the partial computation is deterministic, what? If the entire computation is deterministic, does that not mean that partial computation? I think you said if any stepwise, if any partial computation is deterministic, then it is stepwise deterministic. So does that mean all partial computations will have to be deterministic in order for it to be strong deterministic? I mean, what's the relationship between the two, would you say? Between the strong and
So the relation is not clear at the moment because okay, so it's kind of an question if it's required to ask for stepwise determinism or strong determinism for having the following results. So as a consequence, for instance, we don't have any particular example where we have a stepwise but not strong determinism. But okay, so the strong determinism is really about the probability of each range, whereas the stepwise is that maybe somehow at that state you are doing something which cannot be corrected. Okay, so maybe here these two states are really different, but for some reason after the second measurement then there is a possibility to correct that.
So can you show the definition of partial stepwise?
Stepwise means that
Any, you say any partial computation, then the computation itself can also be a partial computation of the same thing, right?
yes.
So if P is deterministic, then P can also be stepwise deterministic, right? Because it is.
So what is clear is that if it is stepwise deterministic, then it is deterministic. Because any partial computation includes the whole computation. Okay.
Okay.
Mark, got a question on so why is the problem for any angle, say the one you focus on, not for a certain selection of angles? Because you then identify a whole series of problems, which is
Okay, so probably the answer is that if you two possible evolutions. Okay. So if the classical outcome is 0, then in fact we are implementing the projector plus alpha. Okay. We are applying this projector plus alpha to the computation. But if the classical outcome is 1, then we are applying the other projector minus alpha. Okay. We are projecting the state to the state minus alpha. Okay. So these are the two possible evolutions. And in order to make it deterministic, we want to somehow here add a transformation in order to make it equivalent to this one. Okay, we want to close this branching. Okay, and it turns out that it's easy because we just have to apply z here, because we have the property that that z minus alpha is equal to plus alpha. Okay? So if we apply z here, then in fact the operation that we obtain is exactly the same as this one. So if just by applying z, we go back to this hit. So obtaining a deterministic computation is easy. Okay? Take all the measurements and just put a z before. And this z depends on the classical outcomes of the measurement. Okay, you apply z if you are in this branch. So determinism is easy. Okay. But here there is a problem with this description because here we have the measurement and here we have an operation which is depending on the classical outcome of this measurement. And the pattern has to be read from the right to the left. So we are using the classical outcomes of the measurement before the measurement. Okay? So determinism, okay, this is deterministic, but this is not causal. Okay? There is a causality problem here. So, sorry. So, okay, so I say that this is what I said before, that is we are using the classical outcome before the measurement. Okay, so I call it the causality problem. It's just the fact that we are using the classical outcome before the measurement.
And where's the correction of? Why don't you use the correction?
Sorry.
What's with the correction term?
So this is the correction, this is that which is... Sorry.
Because you always have these X corrections. I don't know why, but...
Yes, so we will use the X correction to solve this problem. But this is the first step, okay? Using this trick, we obtain something which is deterministic. And now the problem is how to go from this deterministic but not causal computation to a deterministic and causal computation, a value computation. And in order to do that, we are going to use the structure of the graph, the structure of the entanglement, of the initial entanglement. Okay, so I'm going to use a property of the graph state that you have heard about yesterday, probably, which is that when you have a graph state, let's say this graph, then if you apply x, if you choose any qubit, you apply x on this qubit and then on the neighborhood, then the state isn't changed. Okay. The graph, the quantum state is a fixed point of this operator, x on the qubit and z on the neighborhood. And we are going to use this property now. X, z, z, z is a fixed point of the state. So if we consider this example, here we have the graph state, and this property here can be that if I apply x on qubit 2, this one, and z on qubit 1, this one, then the state isn't changing. So instead of having just N2E12, which is the description of the initial entanglement, I can add these two comments because of the fixed point property. Okay? We can add these two comments without changing the evolution of the pattern. This is the fixed point property. X on 1 qubit and z on the neighborhood. And now, since z squared is equal to the identity, we have the property that z squared is the identity. We get rid of these two z here on qubit 1, and we obtain this term, since this one is unmeasured, then we can apply the correction after the measurement. This is the idea of the correction strategy. Any question? Okay. Okay, so this is just an example, now a more general case. So this is the measurement-based quantum computation. We have already measured these qubits. We are now measuring this one, and these qubits are the unmeasured qubits. Okay? We are measuring these qubits. We know that in order to fight the probabilistic aspect, in order to have a deterministic computation, we can apply a Z here. So this Z is red because it's not causal. Okay? So we know it's deterministic, but it's not a valid computation. So we can use this fixed point property using this qubit here. So we know that I can apply X, Z, Z, Z in order to, without changing the state. So we can remove the Z here, and then we obtain something which is valid because we are acting on unmeasured qubits. Okay, so this is the strategy. So now the question is that what is the property? So this is the property that we want for the graph in order to have a deterministic evolution. Okay, just one remark. If we are using this qubit instead of this one, with the X, Z, Z property, then we have a side effect on this qubit. This is exactly what we want, but we also have a side effect on an already measured qubit. Okay, this qubit is already measured. So we don't want to have a side effect here. So we want to ensure that by using the fixed point property on this qubit, there is no side effect on the already measured qubits. And okay, so we prefer this one. And this condition, the conditions that we have seen previously, has been formalized as a causal flow. Okay, if the graph has a causal flow, I'm going to define what is a causal flow. Then there is a correction strategy. So it means that the corresponding order graph is uniformly deterministic. Okay, so what is this correction strategy? What is the causal flow? So this is what we have seen with the example. So the causal flow is composed of a function f and a partial order. The partial order is describing the measurements, okay, the order of measurements. So here we have qubit u. All the elements which are smaller than u according to this partial order correspond to the qubits which are already measured. The elements which are larger correspond to qubits which are not yet measured. And there is a causal flow if for any vertex u there is a neighbor of u, we call it f of u, and we are going to use this fundamental property on this qubit. So it should be a neighbor of u in order to have a side effect on u. So this is the second condition. And moreover, all the other neighbors should be larger than u in order to avoid the side effect on the already measured qubits. Okay? So this causal flow is a formalization of what we have seen before. That is, we want to use this fundamental property, but in order to use it in a proper way, we need this condition. Okay? We need that the graph has a causal flow. So here it's an example of graph which has a causal flow, so from the input to the output. So this causal flow can be represented as follows. So the function f can be represented as an orientation of some edges. If the corrector of this vertex is this one, then we put an orientation here. If the correction of this one is this one, then we put this orientation, and so on. And the partial order is represented by this set, this partition of the vertices. So these elements here are the maximal elements according to the partial order. This one is another, is the maximum of the rest, and so on. So we can represent the causal flow like this, and in fact the depth in that case is exactly the number of partitions that we obtain. Okay? We can measure all these qubits at the same time, and all these qubits, and so on. So in fact the depth is the number of partitions minus 1, because we are not measuring the output qubits. Okay, so this correction strategy has been formalized using this causal flow, and we obtain correction strategy and the depth of the computation. is partial order over the vertices of the graph, okay, which is just representing the order of the measurements. Okay? And this, it comes together with a function f, which is describing the correction strategy. And we should satisfy the following condition. U has to be smaller than f of u, because f of u is the corrector, so we want to apply the correction on a qubit which is unmeasured. So f of u has to be larger than u. The idea of the correction is to have a side effect and correct the z operator that we have here, okay, in order to make the computation deterministic. So we need that f of u, the corrector of u, is a neighbor of u. So we need an edge between the corrector and u in order to have the appropriate side effect on u. And the last condition says that all the other qubits has to be larger than u because we want to avoid a bad side effect on already measured qubits. So this is the formalization of the previous example.
Could you possibly just go through the example of the third one, the one that was causing a problem before? Because I think that might help.
Yes.
Yeah, with regards to your partial order.
Yes, it's a problem with the partial order, yes. So maybe there is a different partial order.
Could you explain how it's a problem with the partial order? I don't actually quite see.
Okay, so it's a problem with the partial order because here we have a side effect on a qubit which is already measured. So it's here we want to apply the Pauli operation. Since the measurement is descriptive, okay, after the measurement the qubit is just descriptive, so we cannot apply a correction after the measurement.
I realise the conceptual issue. I'm saying with regard on the next slide. You've done an example on U. Could you do that on the other one instead, so that we could see how it gets excluded by the partial order, or is that?
So it's excluded by the partial order because of the third condition, which says that if I take another neighbor of f of u, this one should be larger than u. So if I take, I'm starting from f of u, if I take the neighbors, so this one or this one, they should be larger than u. So if I take this guy, here there is a neighbor here, which is smaller than u. So it violates the third condition. You're welcome. So, okay, so we have the causal flow, which is a sufficient condition for determinism. Okay, it gives us a way to implement the corrections. Okay, so here it's an example of graph which has no causal flow. The idea is that if you, okay, so we want to correct this guy. So what is the corrector of this guy? So the graph is symmetric enough to see that it's the same if it is C or D. So let's say that it's C. So if the corrector of A is C, then because of this H, B should be measured after A. Okay? If I choose C as a corrector of A, I have a side effect on B, so B should be measured after A. Okay, so A is smaller than B. If I choose D as a corrector of A, it's exactly the same. Because of this H, A should be smaller than B. But now, if I look at the correctors of B, if I choose D, then A should be smaller than B. And if I choose C, then A should be smaller than B should be smaller than A. So we think that B is smaller than A. So here there is no solution. Okay. So for this example, there is no causal flow. And the idea is that it's because of this vicious cycle. This kind of cycles, and this, then there is no, with crossing edges, then there is no causal flow intuitively. For the same reason, this one has no causal flow, and the reason is this cycle in red. Okay? Because of this cycle in red, we obtain some constraints on the partial order which cannot be solved. Okay? So this graph has no causal flow. So there's lots of graphs which has no causal flow. Okay, so just so we have this condition, which is that the causal flow is a sufficient condition for determinism, and it turns out that we can check efficiently if a given open graph has a causal flow. There is an efficient classical algorithm for that, and the complexity, the sequential complexity is n, where n is the number of edges of the graph. So it's easy to check if an open graph has a causal flow. It's an to answer this question, let's consider this example. So this is very similar to the previous one, but now there is no edge here. Okay? So we cannot use this guy as a corrector of this one. So since there is, in that case, there is just one vertex which is larger than this guy, I, and which is unmeasured, we should use it. But we have a side effect here on the past, and we want to avoid this side effect on the past.
I thought we had already avoided it with the previous condition.
Okay, but now we will see that we'll see if it's possible to have a deterministic evolution even if there is no causal flow. Okay, so now I'm assuming that there is no causal flow, and I'm trying to see if it's possible to have a deterministic evolution.
So, just one question. So in this example, so let's pretend the last qubits are linear qubits.
Yes.
Here a part which is disconnected.
Yes.
Is the fact that it's disconnected necessary to have such an example?
No, because if it is disconnected, it's not deterministic. It's not strongly deterministic. So the connection is kind of assumption.
This is an example for something which is uniform deterministic but has no fault, right?
Yes, no causal flow. Yes.
So can you find an example which has a connected graph?
Yes, just add an edge here, for instance.
And it's going to be
Yes, it doesn't change what I'm going to say.
Isn't it possible to actually put a causal flow in this graph? The problem is that past Q is on the bottom, and it's measured too early. It's measured later, you can make a causal flow.
Yes, but so for instance, if these two qubits are input qubits, as you say, let's say that these are input qubits, then we cannot use them as correctors. So, and yes, and then maybe we can choose a different order. But here it's just an example. Let's say that the partial order is fixed, and what we can do, can we choose some correctors in order to make it deterministic? It's just an example. Okay. So here we have a side effect on already measured qubits. But the good news is that we can fight this side effect by using another qubit. Okay? If we use this fixed point property on this qubit, then we fight the side effect here. So the idea is that instead of using just one qubit as a corrector, if you use several of them, such that some parity conditions are satisfied, that is, all the qubits which are here are evenly connected to the correctors, such that there is an even number of z, which means no z, because z turns the identity, and such that this one is oddly connected to the correctors, because we want to have a side effect here. Okay, so here the idea is that instead of using one corrector, we are using several correctors, and the previous conditions are becoming parity conditions. Okay, because an even number of z is no z. Okay, so we can use these two qubits in order to do the correction. And so this idea of parity condition is given by the G-flow, generalized flow. So now, we have the G-flow is a partial order, still representing the order of measurements. And now the correction is given by a function G, which is associating with every vertex which is not an output, so all the measured qubits, not just, well, what is this actually? It means a subset of vertices. Okay? We get about this strange notation. It's just a subset of vertices. Okay? We associate with any vertex a subset of vertices, which is satisfying the following property. So first of all, this set should be, all the elements of this set should be larger than U. Okay? This is the first condition. All the elements are larger than U. It means that they are unmeasured. U is in the odd neighborhood, so it means that there is an odd number of edges between U and this set. This odd neighbors guarantees that we have a side effect on U when we apply this fixed point condition on all these vertices. And finally, all the other elements which are in this odd neighborhood has to be larger than U. So in other words, the last condition says that all the elements which are smaller than U have an even number of edges between each of them and the set G of U. So here there is no edge between this guy sufficient condition for determinism. If there is a generalized flow, then we know how to construct a correction strategy in order to have the uniform determinism. And here is an example that you have already seen, and we said that there is no causal flow for this one because of the cycle, because of some cycle here. But it turns out that for this particular graph, there is the G flow, which is described here. So the correction of A is just D, and the correction of B is DEF. B is DEF, so we can see that there are 3 edges between B and DEF, so the parity condition, there is an odd number of edges between B and DEF. And if you take A, there are 2 edges between A and this one, so this condition is satisfied as well. And C, there are 2 edges. Okay, so this is the correction of B, and the correction of C is DF. Okay, so it satisfies the G flow condition, and in that case, the partial order is such that there are 3 parts in the partition induced by the partial order. So the depth of this example is 3 minus 1 is 2. So since we have an example which has a G flow but no causal flow, it means that the causal flow is not necessary for determinism. There are particular graphs, like this one, for which it's possible to have a deterministic evolution even if there is no causal flow. And the good news is that we prove that this G flow condition is in fact a characterization of the uniform determinism. Okay? There is uniform determinism if and only if there is a G flow. So this is a characterization of the determinism, the existence of a G flow.
In a sense, we're most interested in getting the good criterion for determinism, right?
Mm-hmm.
So this is, I guess, this is not necessary for deterministic.
No. This is the technical part where we need to add the uniformity, the strong, and the stepwise determinism in order to have this equivalent. Okay? If you just look at sufficient condition, then it's a sufficient condition for determinism. But if you want to have the other way around, you need to add some conditions. This is where we need stepwise and so on. Okay. So there are graphs which has.
That's okay, I wanted to ask him down the previous slide. How does the fact that G of C equals DF satisfy the parity condition?
So the parity condition here, so if you look, so C and DF. So between C and DF, there is just one edge, this one. Okay.
Okay.
And for B and A with DF, B, there are 2 edges. So it's even. And for A, there are 2 edges, so it's even as well.
Okay.
So this one is oddly seen, the other ones are evenly seen, so it satisfies the condition.
Awesome. Thanks.
Okay, so there are graphs which has G flow but no causal flow. So it's interesting, but in fact, even if the graph has a causal flow, it's useful to use the G flow in order to have a speed up, in order to decrease the depth of the computation. Here we have an example. So it's just this pattern which is repeated like this, okay? And it turns out that there is a causal flow in that case. The corrector of A1 is just B1, then the corrector of A2 is B2, A3 is B3, and so on. But because of this edge, when we correct A1, we have a side effect on A2 using the causal flow. So it means that A2 should be smaller than A1 should be smaller than A2, should be smaller than A3, and so on. So we have this, and as a consequence, the depth of the computation is n. Okay, because we have lots of conditions of under partial order. So there is a causal flow, but the depth is n. And it turns out that there is a G flow here, such that the depth is just 1. So the partition is just a bi-partition. How it works? The idea is that in order to correct the qubit A1, we are using all the qubits here. We are using all the qubits. And if you look here, A2 is evenly seen. If you take all the qubits, and in fact all the AIs or I's larger than 2 are evenly seen. And this one is oddly seen. So it's a valid correction set. And for A2, we are taking all the qubits BI with I larger than 2 and so on. And we obtain here G-flow in order to decrease the depth of the computation. So, and what about the algorithm for deciding if whether a given orthograph has a G-flow? There is also an efficient algorithm. Okay, so this condition, the G-flow condition, is also easy to check. For a given graph, deciding whether this graph has a G-flow, it's easy. There is an efficient classical algorithm. Okay, so now, so maybe it's a good, if you have a question, yeah?
Can you give us some simple characterization in terms of graphs, like tree graphs, has G-flow or connected? Can you give an answer in standard language of the graph theory?
Okay, so if you have a tree, if the input is the center of the tree, is the root of the tree, and the outputs are the leaves, then there is a G-flow. Yeah. Yes. Okay, so now I'm moving to the second part, which is the computational depth complexity of NBQC. What this means that now we are going to compare the computational power of this model, of the measurement-based quantum computation, with other models of quantum computation, especially the quantum circuits. Okay. We are comparing quantum circuits and measurement-based quantum computation in terms of depth of the computation. So, first some remarks, some known results about this comparison between measurement-based quantum computation and quantum circuits. First of all, it turns out that any Clifford operation can be implemented in constant time, in constant depth in the one-way model. So I think that Martin talked about it very briefly yesterday. So maybe just the idea of the proof. So two facts, to prove this one. The first fact is that if you want to implement a Clifford operation, so a Clifford operation is just a circuit, a quantum unitary, which is obtained by combining H, control naught, and Pauli operations, if you want, X, Z. Okay. So if you are using just this gate, then you will have a Clifford operations. And it turns out that in order to simulate these gates, we only need measurements of the form 0, or I over G. Okay. So it's just a fact. In order to simulate a Clifford operation in the measurement-based model, we only need this kind of measurements: 0, angle 0, angle pi over 2. Yes.
Would you mind restating the definition of a Clifford operation, please, and give an example of a non-Clifford operation?
Okay, so the definition is this. We have a Clifford operation if you can describe, if there is a circuit where the operations are C0, H, X, and Z, just C0, H, okay? If you combine C0 and H together, you obtain a Clifford operation. And an example of non-Clifford operation is just a rotation of angle, I don't know, pi over, should be enough, pi over 8 should be enough. So if you, yes, if you have, oops. So for instance, the one unit operation here, this one should
Yeah,
be
so I guess
Clifford operation.
why exactly would it not be Clifford?
Okay, so Clifford is just a special class of unitary evolutions. Okay, so they are obtained like this, and it turns out that it's not a universal set of quantum computation. Okay, if you want to implement an interesting algorithm, you need non-Clifford operations. Okay, so it's just a simple subclass of operations. Okay, so first remark, we can implement any Clifford operations just by using these two numbers of measurements. And if we are using this, and the fact too, is that if we are using these measurements, so if alpha is equal to 0, in fact, we are performing measurements in the diagonal basis, plus and minus And it turns out that if we have a measurement, and if we apply x to plus d plus, x to minus d minus, z to plus d minus, z to minus d plus. So what does it mean? It means that if we have a measurement on some qubit I, such that the angle is 0, if before this measurement we have a correction, let's say the x correction on this qubit, which is depending on some signal classical outcomes xj, in fact x is not changing the basis of the measurement. Okay? It preserves the basis of the measurement. So in fact, when we have this is equivalent to just have the measurement. Okay? In that particular case, we can just remove the correction because the correction is not changing the angle of the measurement. Okay? And if you have z instead on this qubit, then in fact you are just exchanging plus and minus. So in fact the basis of the measurement is the same, it's just the interpretation of the classical outcome which is different. So you can just change the interpretation of the classical outcome. So you can replace this quantum correction by a classical correction. Okay? And if the angle of the measurement is pi over 2, we have something similar, except that the role of x and z are exchanged. Okay, so the idea is that when you have just this kind of measurements, you can remove all the measurements, okay? Sorry, all the corrections, okay? And you obtain something which has no correction, and as a consequence, okay, so this is the last step of the proof, since there is no correction, you can implement it in a constant depth. Okay. Okay, so Clifford operation can be done in constant depth in the one-line model. And it turns out that if we look at the quantum circuits, it turns out that we have this result in Aronson and Gottesman, which says that any Clifford can be implemented in log depth. Okay, so here there is a difference, constant log. And it turns out that there are some particular Clifford operations which are really requiring this log depth. And the example is the parity gate. So the parity is this gate. Okay. So you have 10 inputs, and the first n minus 1 outputs are just unchanged. And the last one is the parity of the previous one, that is the sum modulo 2 of the inputs. Okay, so this is the parity. Here, this output is nothing but the parity of the number of ones in the input. Okay. So this is the parity gate. So it turns out that this is a Clifford transformation. And in order to perform this parity gate in the quantum circuit model, we need a depth which is logarithmic. Okay, so here there is a separation between the two models. So this is just a fact.
Can I just check that's been proved that you can't do it in less? Is that right?
Yes, you can do this. And the idea, basically the idea is that since this output is depending on all the inputs, we need at least log n steps in order to have the influence of all the inputs to the output. Okay, this is the idea of the proof. So the question is, what is the exact power of the one-line model, of the measurement-based quantum computation? Sorry. So what's the from this set of universal gates. So the control Z here, here an arbitrary rotation, and here the Hadamard gate. We are using circuits with ancillary qubits. So here, in fact, this one is the non-input qubit, and this symbol means that this qubit is initialized in the state 0. And this symbol means that this qubit is the non-output qubit, so we trace out this qubit, or equivalently, we measure this qubit in the standard basis. Okay, so we are using these quantum circuits. Notice that here there is no classical control. Okay, it's not possible to say that okay, I take the classical outcome of this measurement and I use this classical outcome for something else. It's not possible. Okay, it's not in the norm. When we are measuring a qubit here, we are losing the qubit and the classical outcome. Okay, so what are the connections between quantum circuits and measurement patterns? So we have this first result, which says that if you take a quantum circuit, you can simulate it by a pattern, and the size of the pattern is essentially the same as the size of the circuit, and the depth of the pattern is the same as the depth of the circuit. Okay. So you are not increasing the depth and you are not increasing the size if you take a quantum circuit and you simulate it in the measurement-based quantum computation. The idea of the proof is just by composition, because each gate of the quantum circuit can be simulated by a piece of pattern of constant depth and constant size. Okay. So then just by composition you obtain a measurement pattern which has the same size and the same depth as the previous quantum circuit. So this is one side. What about the other way around? Now I have a measurement pattern, so a measurement-based quantum computation, and I want to simulate it using a quantum circuit. So in that case, so the size is increasing, but we don't really care about the size here. What is important is the depth. Here the depth is also increasing, and we have this log factor. Okay, so we are increasing the depth with a log factor. The circuit has a depth which is larger than the depth of the measurement pattern.
Are you assuming you have special graphs now with the flow?
No. It's just any measurement pattern, even non-deterministic patterns. Okay, so what is the proof of these results? So now we are simulating measurement calculus using quantum circuits. So in order to simulate the creation of an ancillary qubit, we are just using this. That is, we create an ancillary qubit. And since it's not an initialization in the same state with like h, in order to go from the 0 state to the plus state, okay, it's just a qubit initialization. Eij it's nothing but the application of control Z, and we have control Z in the quantum circuit, so it's very simple. Now the measurement, how to do a measurement in this basis, which is parameterized by the number alpha. So we are using the measurement in the standard basis of the quantum circuits, and we are just changing the basis. Okay, we rotate the basis in order to have the appropriate basis, and this rotation is given here. So we apply h followed by the rotation of some angle minus alpha. Okay, so we can simulate this measurement by this piece of circuit. Okay, so the problem is how to simulate the correction. So here I have a correction on some qubit 2, this qubit, which is depending on the classical outcome of the qubit 1. And so we can write it like this. So this is the simulation of the measurement, the correction. But here this is not a valid circuit, because here I have a classical outcome. And there is no classical data in the quantum circuits. So a very, very usual trick consists in transforming this classical control into a quantum control. Okay. In fact, we postpone this measurement and we replace the classical dependency by a quantum control, and we obtain the control Z.
Yeah, but that is just as equivalent as having classical control.
Yes, it's equivalent, but we obtain a valid quantum circuit, whereas this one is not a valid quantum circuit.
Yeah, but well, I guess I'm saying it's just the principle of today measurements. I'm not sure why.
Yes, it's a very, very standard technique, I agree. But But we'll see what's happening, what's the problem with this. Okay, so now what's happening if there is a dependence on several classical outcomes. Okay, if this correction is depending on several classical outcomes, then we take this piece of circuit. Here it's qubit 4, so we apply Z, but it's depending on 3 classical outcomes, so we obtain here qubit 1, 2, and 3. Okay, so with just one command here, we obtain a piece of circuit which is not of constant depth and constant size. Okay, this is where we have a problem. So this one is, so the size and the depth of this one is linear in the number of corrections, but it turns out that we can implement this circuit with the logarithmic depth, because this is a Clifford circuit, and we know that Clifford circuits can be implemented in log depths. So we can take this circuit, rearrange, add ancillary qubits if we need, and we obtain the log depths for the simulation of the correction.
There's some questions. So you remarked at the beginning of the lecture you're not going to count the classical depth on the summation of your
Yes.
And maybe something to be implemented, I think, at best in low depth.
Yeah.
So it's usually the same thing, is it not? The
Yes,
low
yes,
depth
yes.
is the low depth of the classical overhead, which you're not counting because it's not counting.
Yes. Yes, yes. It's okay. So here everything is coming from the assumption that we don't care about the number of inputs here, and it turns out that in order to classically compute this sum, we need a log depth. So if we take into account this, the classical computation, then we obtain the same depth. Okay, so we can, so the picture is like this. So if we are defining these classes of complexity, Q and C, K, which is the class of, so they are already known classes. So Q and C, K is the class of problems that can be solved by quantum circuits, such that the depth of this quantum circuit is log Kn. Okay, so logarithmic depth, log K depth. So, and here Q and C, K is the class of problems that can be solved by measurement patterns of depth log K. Okay, so the two classes corresponding to quantum circuits and measurement patterns, and we have the following inclusions thanks to the previous results. We take a quantum circuit, we can simulate it by a measurement pattern without increasing the depth. And if we take a measurement pattern, we want to simulate it by a quantum circuit, we are increasing the depth with the log factor, so we obtain K plus 1. Okay, it's just to sum up the previous results. So we have these inclusions, and in fact there is just one inclusion which is known to be strict. It's for K equal to 0. It's this one for K equal to 0 for the parity gate. We know that the parity is in Q and C 0 because it's Clifford operation, but it's not in Q and C 0. But in fact, for all the other cases, we don't know if the inclusion is strict or not. Okay, so to sum up the resources that we are using. In the quantum circuits, we are using the standard resources 1 and 2 qubit unitary transformations. In the one-way model or measurement-based quantum computation, we are using some standard resources, 2 qubit unitary transformation, 1 qubit measurement, some corrections. But the big difference is that we are using this unbounded parity, which is a classical operation. Okay, this is this sum, and we assume that we have it for free. So this is the assumption that we have here, which makes this model more powerful than the quantum circuit.
Unbounded, you mean that K can be very large, right?
Yes, K is yeah. Okay, so it's related to the fact I said at the beginning, we talked about it a few minutes ago, the fact that this kind of comments is of size 1 and depth 1, whatever the number of classical outcomes we have here. Okay, so it's not surprising that this model is more powerful than this one, because we have this. So it's kind of unfair. So now the idea is to add to the quantum circuit a new resource in order to have a chance to have two models which are equivalent. Okay, and what we are adding to the quantum circuit is the fan-out gate. Okay, so now we are considering the fan-out circuit. So the usual circuit plus one gate, this fan-out gate, okay, which is defined as follows. So this qubit is unchanged, and all the other ones are taking plus x. So this is called fan-out because if you see all these qubits are ancillary qubits which are in the 0 state, and this is the unitaries in the circuit model. And it turns out that if you are using this extra gate together with the other gates, then it's possible to simulate to have a constant depth implementation of the parity. I let you as an exercise, it's not very difficult, but if you take this fan-out gate and you apply H everywhere, then you obtain the parity gate. So it means that we can implement the parity gate in 3 steps. H, then this gate, fan-out gate, and then H. It's the other way around, superposition. H, fan-out gate, H. Okay, so we can implement the fan-out gate in a constant depth. So like in the measurement-based computation. Okay, so it seems to be, so these two models, quantum fan-out circuits and measurement-based computations, are equivalent at least for this problem, the parity problem. And it turns out that they are equivalent in general. We have the equality of these two classes. So QMSC K is what we have seen before, class of problems that can be solved with a depth log K in with a measurement pattern. And this one is a class of problem that can be solved with a quantum circuit with fan-out gate, F is for fan-out gate, in the depth log K. So if we allow this fan-out gate, then we have exactly the same power. Okay, so this is, I think this result is more surprising than the previous one. Okay, because we are working with different kind of resources, a quantum fan-out gate or a classical parity, and in fact it leads to the same computational power. So the proof is here, so very briefly, we'll probably skip it. Okay, so this part is easy. So you take a circuit and you want to simulate it using a fan-out gate, using a measurement-based quantum computation. So we already know that all the gates but the fan-out gate can be simulated in constant depth. And since the fan-out gate can be implemented using the parity, and we know how to implement the parity in constant depth in the measurement-based quantum computation, we obtain that all the bicompositions, since all the gates of the circuit can be simulated in constant depth, we obtain a measurement-based quantum computation which has the same depth. Okay, so I'm not going to the details of the other parts. Just one point. So it's very similar to the simulation of the measurement-based quantum computation with quantum circuits. Okay, but in the quantum circuits we have seen that we have this for the simulation of Z, S1, Sk, we obtain a piece of circuits. Okay, with lots of control sets. Okay, if you remember. And it turns out that the depth of this thing is logarithmic. And the good news is that here we can use this result, which says that if the unitary is diagonal, then we can simulate it in constant depth with a fan-out circuit. And it turns out that the control Z is diagonal. So here, even if we have lots of control Z, this is a diagonal unitary. So we can use this result in order to simulate it in constant depth using the quantum fan-out circuit. And so for X, we obtain control X, it's not diagonal, but we can work and transform it using H's, and we can also simulate the X corrections in constant depths. So this is the result of the equivalence between the two classes. So to sum up, if we look at the resources, so we have the standard quantum resources here, and these two extra things, here the classical parity gate for free, unbounded, and here the quantum parity gate for free, unbounded as well. And it turns out that these two models have the same power in terms of depth complexity. So what is surprising is that, so the message is, in a standard quantum setting, that is if we have these gates, all these gates, 1, 2 cubic measurements, unitaries, in fact the classical and the quantum unbounded parity gate have the same computational power. Okay, so it means that, classical or quantum are equivalent for this special case. Okay, so since the measurement-based quantum computation is equivalent to quantum circuits with fan-out, we can use this interesting paper which says that quantum fan-out is powerful by Fourier and Perdrix. And since this is equivalent to measurement-based computation, the idea is that the measurement-based computation is powerful too. And what it means that you can implement these logical gates constant depth with a measurement pattern. So, and all these results together, you obtain that the factorization can be implemented is in this class. So what does it mean? So RP is random polynomial, so it's classical class, the classical class of problems. So if you have a classical randomized computer which is using constant depth measurement-based quantum computation, here the B is because here we have some approximated version, we don't really care about that. So if you have this constant depth measurement-based quantum computation together with a classical computer, randomized classical computer, then you can implement the factorization. So it's a very interesting result. Okay, so to sum up, so we have seen that this equality, so it means that this measurement-based, we have captured in fact the power of the measurement-based quantum computation. It's exactly the same as the fan-out quantum circuits. We have this interesting result. So yeah, it's interesting to have the factorization in this class. And we have this interesting message, which is that if we have some standard quantum settings, then the classical and the quantum unbounded parity gates are equivalent. So it's surprising. The open questions is, so first we have the separation of these classes for k larger than 0. That is for k larger than 0, is it really more interesting to use measurement-based quantum computation instead of quantum circuits? And Richard's conjecture, which is that if you take any polynomial time quantum algorithm, then you can implement it using only a logarithmic number of quantum layers together with classical polynomial time computation. Okay, so it's not, we don't have the proof of that using the previous results, but it's the objective. Thank you. Have any questions?
Are there any questions, comments? Yes.
Maybe I missed this part, but is there a measurement pattern for the fan-out?
For the fan-out? Yes. Yes, because the fan-out gate is a Clifford gate. And so we can implement this in the measurement-based quantum computation with constant depth. So
Is there?
it's simple. It's simple. Okay. I think. The graph state for implementing the fan-out gate looks like this. Okay. So the input, the output, and here are some edges, some extra edges, and if you perform 0 or pi/2 measurements in the appropriate position, then you obtain a simulation of the quantum fan-out circuit.
Okay, this is a very simple one. So if I recall correctly, initially the definition of the problem only had E, M, and C components, right? And is there any particular reason why you added the M later?
No, there is no very, very important reason. If there is no En comments, then you don't know which qubits are the inputs and which qubits are the ancillary qubits. So you have to specify it on the side, okay, to say that these qubits are the input qubits. If you are using the N comments, then you have all the information just in the pattern.
Yeah, but that used to come with the other part of the pattern definition, which was the vertices, the set of